Okay.
Hi everyone, again, thanks for going to the first lecture and deciding it was worth it to come back. It's always nice. I think everybody was either here or you watched the video. So I don't think I really need to do a recap of what I said. As you know, the main point of this course is to really emphasize the role of the phasing wave function in quantum mechanics. And this week we're going to start off with the sort of fluid description of position space quantum mechanics. That's basically a reformulation of what you did in 115A. So in order to do that, I think it's probably a good idea to explain just like some very basic fluid mechanics, because it's not something that you really do that much in lower divisions, at least I don't think. And even if not, then it's a good review, and I wouldn't say that I'm going to be doing like a strict derivation of these. It's more sort of explaining what they mean in the context of sort of simple fluid. So let's say basic fluid mechanics as a start. I'm basically going to be covering two equations. The first equation is the continuity equation. So you can imagine, like, if you have a fluid, I don't even know if I need to draw this. Let's say you have something that's got like water or something, right? And the density of this may be higher in some regions and lower in some regions. But overall, assuming we have overall we would have conservation of mass. So you could say, like, assuming that no fluid is flowing in or out of the system, that the fluid is going to remain with the same mass. So what we can do is we're going to consider, well, we have this sort of closed system. Let's consider an open subsystem that's, say, like in the middle of it here. So I'm just going to consider this region. And if I want to find the total mass of this, let's assume it lives in 3D space, then I can just say, call the mass of, let's call this little region having mass m. We can just say that the mass is going to be the sort of triple integral over the volume, maybe call the volume V, of the density of the fluid, and then integrated over the volume, which I'll use the Lake-Griffiths notation, which likes to use tau as the volume element. Which is a little bit curious, but I think it does at least avoid confusion as if I said like dV or something. Okay, so then this is, this has some mass, but because this is now like an open system, it's not the whole fluid, there might be fluid flowing into it or flowing out of it at any given time. And so we can consider that this mass is really like a function of time.
And rho is a mass density.
Yeah, let's maybe go. This guy is the mass density. Right, so this is, if you've taken 23, 24, it's like just replace math with charge, and maybe that would make it even easier, because this is pretty much exactly what you do when you start talking about that. So if this is a function of time, we consider, well, what is the sort of inflow and outflow of the mass over time? We can just take a derivative. So we can say dm dt is equal to something. The sort of, I think the Leibniz rule is what it's called, right? When you have a total derivative, or say a full derivative of this mass as a function of time, and you pull it inside this integral where this volume element is kind of, not really depending on time, you can change this to partials. So we integrate over the volume of the time derivative of the mass density with respect to the volume, right? So this is, so far, just very simple vector calculus that you may have done in like Math 4B or something. Sorry, let me speak up. I have a little bit of a cold. So, tell me if you can't hear me. So the next thing that we want to do is we want to sort of relate this quantity to a different quantity, and that's going to give us the continuity equation, which you guys probably already know what the form that's going to be. So if you imagine that you have, again, this region, in order for the mass of it to change, you have to have the fluid from inside the region to flow through the boundaries. So you have to have flow out through the boundaries, or you could equivalently have, or not equivalently, but you could have, fluid from the outside flow into it, right? So if we consider the, let's say, the flux through some area, let's say, it's hard to draw, maybe if I draw this in 3D. Okay, so suppose this is something, and then I'm going to consider the flux through like this area as the fluid flows through it, and then we just integrate that area over the whole surface. That flux is just going to be, maybe let's call this, let me call this guy ds, say for like a surface element. The flux through ds of, let's say the flux, this is like the fluid flow, is just going to be given by the density of the fluid, right? And then just dotted with the, because that's sort of how much is going here. And then, I guess this is a vector, this is pointing out. And then we just consider how much is flowing through is just going to be the velocity dotted with the area element. Is that clear to people? I don't know, maybe that's a little bit of a jump. That's good. Okay, cool. So we could find the total outflux through this as, let's say, yeah. And we're considering, let's say, the outflux here. We could find out the total outflux through that by simply saying that this is equal to the integral over sort of the surface of this, so call that S, of just rho v dot es, right? And then using, I think the divergence theorem, right? This is the same thing as the integral over the volume V of just, what is this? Rho v, divergence of rho v dotted with, sorry, not dotted with, dv.
I use velocity.
Yeah, sorry. This is, the vector v is velocity, and then this, maybe I can try to make it like a script v to make it kind of looks like a new now, but. And this should be equal to minus m. Right? Does that make sense? Because we're kind of considering how much is flowing out. Okay, so then you can equate, let's see, sorry, not minus m. This should be, because it's at any given time, it should be minus d. Okay, so then we just equate these two, and then we say that, well, this holds for any volume V within the fluid, so we just equate the two integrands, and we find that sort of our first thing that we care about is the continuity equation, which maybe I'll write here, it's a box, because it's important, is that the time derivative of the mass density, or just a density, plus the divergence of the density times the velocity, that's a divergence, is equal to 0. And we can identify, or often we will identify, let's see if this chalk is good, this thing as the current, call this J, or the current density. Okay, so that's one. This is what you're familiar with, it's the continuity equation. Should seem pretty familiar. Again, if not from fluids, it should seem pretty familiar from like electrostatics, or electricity and magnetism. So that's the first one. The second one is the one that you maybe are a little bit less familiar with. So let me describe it. This one, it is like I didn't really derive it, I kind of just stated this, and it's kind of the connection between this and this is what you need to get the continuity equation. But it's like a compact statement of the fact that there isn't just conservation of mass, but there is continuity of mass in that you can't just have mass disappear somewhere and then appear at some delocalized point from that instantaneously. You need to have some flow for that to happen over some amount of time. But so that's kind of like a preliminary, it's a restatement of our condition of continuity. It's a statement of our condition of continuity. The second one is going to sort of more so govern the dynamics of this fluid, and that's primarily going to concern the velocity field of V. So, okay, this is what's going to be called the Euler equation. And in order to deal with that, we're going to need to do something that is a little bit conceptually weird. So previously here, I was considering like a fixed volume V, and I was considering mass flowing in and out of it. And you can derive the Euler equation using that, but it would, I think you kind of require to do this in Lagrangian formalism. So instead, what I'm now going to shift frames to is I'm going to say, let me consider, like, again, say this volume V, but suppose it's some infinitesimal volume. And suppose that infinitesimal volume, we're going to sort of consider how that volume now is changing and flowing over time. So we're going to consider like this density is going to over time move, and we'll just choose it small enough so it doesn't spread out into like a fractal or something. We'll assume it's a continuous fluid, so we can always do that. If you say that, then the mass of the volume M, right, is constant. And if we just want to write Newton's second law, we can just simply say that this, right, so this is just the change of the momentum, is equal to, assuming no weird non-conservative forces, can be written as minus the gradient of some potential, where I can say maybe, let's be clear that this is like this. Or you know what, that'll make it weirder actually. Let's just say this is some, that's a bad V. Let's say phi, so that we don't confuse ourselves. This is just Newton's second law stated.
That's a pressure.
Yeah, it's a pressure. It's whatever. Yeah, so I guess this is a force on an infinitesimal thing. So it's a force per, right? So then it's a pressure. I'm just thinking of it as like a force on an infinitesimal. Because we're now thinking of the fluid chunk as like moving through space. This velocity really is really a function of x, where x is the position of that little blob of fluid, and that is a thing that varies in time. So it's a function of x of t and t. So when we take this derivative, we're going to have to act with the multivariable chain rule. Right? So this becomes m times the partial derivative with respect to v, or of t with respect, of v with respect to t, plus v dotted with a gradient on v, or maybe, wait, let me, the reason why this is happening, the v dotted with a gradient is because you take the derivative with respect to x times the derivative with respect to t. So let me write that. This is dx dt dotted with dv dx. But this I'm going to write as this is v, and then this is the gradient of v. So it's like a directional derivative. So this becomes v nabla v. Okay, and then this is equal to minus gradient v. And this thing, the fact that you have this extra term that's like that has to deal with the velocity field, like how much it's moving, means that this whole thing is sometimes written as capital dv dt, and it's called the convective or the material derivative. If you ever study fluid mechanics, then you will definitely see this notation. And we will come back to it later. So that's, see, I spent 20 minutes on that, that's good. So these are the two important equations of motion for a fluid. This one, as you can see, is literally just Newton's second law applied to a moving velocity field that behaves a little bit unsugarly because of the standard active derivative, but it's pretty much just Newton's second law. And this is the Euler equation. Right. So I was going a little bit slower at the beginning just to let people catch up, or to let people come in. Does anybody have any questions on this before we actually move on to the quantum mechanics that we're here for?
Can you explain the physical setup again in writing Newton's law? Is that just saying you have some?
I'm just saying that if you have, so okay, I'm now thinking about this like block. Think this is some like infinitesimally small thing. It is moving through, like now I'm thinking of the blob as moving. And the reason why it's moving is because there's a force acting on it. Right? It's like from the velocity, either because there's like fluid pushing it kind of, or there's like some external like pressure. Like there's a force that's pushing it, which is like the pressure.
Sure.
Right? Yeah.
Wait, so when you said that the blob was a closed system, what did you mean by that?
Sorry, the blob, the closed system wasn't the blob. The closed system is the whole.
The whole
fluid.
blob.
I was saying before,
Yeah.
I was saying we have a closed system, and now I'm going to consider an open subsystem within it. That's all I was saying. Yeah.
Okay.
So there's, this is the external force, but then because the fluid is also flowing, there's like this extra term that shows up. Does that make sense? Okay, cool. So, we're gonna rewrite basically these, we're gonna literally derive these two equations, but instead we're gonna get them from the Schrodinger equation. And it's going to be for a quantum fluid. So that's the goal of today's lecture. If you look in the notes, let's see, I don't know if I actually have time to do this today, but there's a whole discussion of Galilean relativity that we may or may not get to. Let's see. It's 10:20. I think we can probably do it. Yeah, I think we can do it. Okay. I may skim over some algebra at one point if we get close on time, but I think that it should be doable. Yeah, what's up, Jensen?
I still don't see the notes on Canvas. I only see the week 1 notes.
Sorry. It's kind of weird. It should, oh my bad. I need to publish the module and the IM. Okay. Reload it in like a minute and tell me if it's not there. You can tell me again. Is that good? Okay, yeah. Okay, so pivoting now to quantum mechanics, we want to consider the Schrodinger equation and write it like this. So what is the Schrodinger equation? The one that you're familiar with. It is minus h bar squared over 2m times the, because in my notes I do just position space, or like one-dimensional. I'm going to just work in one dimension, but everything that we're going to do could be very, very easily generalized by just replacing derivatives with respect to x with a gradient, and then it would be the same thing. So it's second derivative with respect to x of the wave function psi plus some potential, which I guess we'll call phi, which, yeah, because I don't want to confuse with volume. Let's call it, okay, I'm gonna, at risk of making it confusing, I wanted to say v, so I'm gonna call this v, and then maybe we can just call this v, and you guys understand that this is supposed to be a potential energy.
Capital V.
Yeah, I don't know, quantum mechanics doesn't like to use U for this term, I guess because of interactions, it's like mutual interaction terms, but this is the one that you're more familiar with. So it's like this is equal to, this is the Hamiltonian acting on psi, so can anybody finish what the right-hand side is supposed to be for the Schrodinger equation? In like specific
h bar d over dt.
Right, and then on psi. Okay, so in order to change the form of this thing, yeah. So I'm still deciding if I want to do, I spent more time on this than I expected. Okay, let me first take a slight detour actually. A slight detour because I want to discuss a little bit of a problem with this that you may not have seen that will be very easily solved or very intuitively solved by this sort of fluid formulation. So I want to consider a Galilean transformation on this thing. Because, as you know, for say, let's just consider, say, a free particle at first, so we can just ignore this basically. So this is the Schrodinger equation for a free particle. A Galilean transformation on a free particle shouldn't change the equation of motion of the free particle, right? So if you, so like say classically, the equation of motion is just like m times x double dot is equal to 0. So if you send x goes to x minus v naught t, where v is some, we can even make this just a 1D thing, where v naught is some constant, then m times x minus v naught t double dot, right, is going to be equal to just m times x double dot, which is going to be equal to 0, and these are the same equation. So classically, the equation of a free particle is unchanged. I want to consider what happens when you deal with quantum mechanics. And we're going to consider what happens to the Schrodinger equation for a free particle, because it shouldn't change. The equations of motion shouldn't change. So when we do this, we have to transform two things. We have to send, right, x goes to, let's call this x prime, right, is equal to x minus v naught t. So that means that partial with respect to x has to go to partial with respect to x prime somehow. This isn't going to exactly say, but we need to sort of shift this to x prime. Let me maybe not do this. We need to send partial with respect to x, partial with respect to t, and psi to, say, this set, to a set that consists of partial with respect to x prime, partial with respect to t prime, and psi prime. Because these are the things that depend on like our position and our time. Is that clear? To do this, the derivatives are a little bit tricky because, well, I guess let's maybe make it clear. Remember, t goes to t prime, which is equal to t in a Galilean transformation. So when we take the partial with respect to x, say, really what we're saying is we're doing that with t fixed. So in order to really understand how we can express this quantity in terms of prime variables, we should act it on some test function. So let me just say partial f with respect to x. I want to write this in terms of just the primed derivatives. So to do that, I'm going to say, well, it's definitely, we can just start off with partial f with respect to x prime. But then we also need, because of the multivariable chain rule, right now we have these defined in terms of each other, we need the partial of x prime with respect to x. And then, yeah.
Is the partial derivative of t prime going to be different from the partial derivative of t?
Yeah, so well, that's why I kind of did this set notation. Yes, that's correct. We'll do that in just a second.
But in Galilean, despite t prime equal to t?
Yes, yes. It's weird, yeah. It's weird, but that is correct.
Okay.
And it will look pretty much exactly the same as this convective derivative term, kind of, because it's kind of like you're moving, so you have like a velocity that's tied to it. But the easiest way to see that is through like the chain rule, and you're right.
Okay.
So let me just do that. This thing becomes this, but then you also have t prime because x is expressed in terms of x, like x and t prime. So we would have partial f with respect to t prime times partial t prime with respect to x. This is 0, so that's 0, and then this is 1. So yeah, in this case he's right. This derivative doesn't change, but as Kareem was going to say, this story changes when you do the partial of f with respect to t in terms of t prime, right? In terms of x prime and t prime. So now if I do partial f, partial, let's say I'll do x prime. So partial x prime times partial t, partial x prime, partial t, plus partial f, partial t prime, partial t prime, partial t. this thing is 1, so maybe let's not call it 0, that goes to 1. But this thing is not 0. This thing is v naught, right?
Isn't negative v naught?
Yes, you're right, that's negative. So this is actually, if we write it, we have the partial of, well, it's minus v naught, right? So we would have partial with respect to t prime plus, or minus v naught times the partial with respect to x, acting on this function f. So yeah, we have a non-trivial thing. You'll notice basically I was to replace the v naught partial with respect to x with the divergence. It would look pretty much like this, except for the minus sign. And the minus sign is because I chose to make v naught negative.
Should be x prime maybe on the...
Yes, it should be x prime. Okay, so this non-trivial factor is going to cause us issues. Oh, I can do that. Because what would you expect psi prime to be equal to? If I really write psi of x, psi of x and t is going to go to psi prime, right? What would you think that psi prime is going to be equal to? Let's say psi prime of, you would think that psi prime is going to just be like the wave function as a function of x prime and t prime. Right? Like this is kind of the intuitive idea that all you need to do is you just need to consider the wave function in the new coordinates, and then, well, it should all work out. But and tell me if you need me to go through the algebra for this. The issue is that when you have this derivative is fine, but if you don't change psi at all, then this time derivative is going to change. So you're going to have this extra term. And that extra term is literally going to change the Schrodinger equation, which means that, assuming we did this right, which this is correct, then it cannot be the case that the wave function just transforms like this. You somehow have to change something about the wave function. And it's not really obvious, at least immediately, what that is, right? And this is going to be the phase. So does anybody want me to exactly work out this thing, like why this is invariant, or is that clear? So did you
Can you do it?
Yeah, okay, so I can say, do you see this term isn't going to change? If I change this to a prime variable and this just to this would remain invariant. This would change because the time derivative gains this extra term. So this is completely the same. This gets one extra term. So let's say this thing, if I say under a Galilean boost, say x goes to x minus v naught t, becomes I h bar times partial with respect to t prime minus v naught partial with respect to x times psi. So this thing is going to stay the same. I could just replace it with a prime, but this is not. And that means that our equation is not invariant. And that's a huge problem because the free particle should definitely be an invariant equation. If v, for example, like if it wasn't a free particle, that's why I changed this. If v is like, if in one term you have a moving potential versus not a moving potential, then there's not a reason for it to be invariant, but it is certainly an issue with the free particle. Okay, so how do we resolve this? Like Ori whispered, we're going to have to change the phase somehow. But how? It's like very, you could probably work backwards. You could say, oh, consider how does the phase exactly have to change by going like this? But to be honest, I feel like that is kind of, it's like ad hoc, right? It's like, well, you did that to solve this problem, but I don't really see why you would do that in the first place. So in order to understand why you have to change the phase, that's finally why we're going to be doing this. So that's the motivation that I wrote when I first wrote these notes. Though honestly, you don't need that as motivation. Okay, so let's call that, let me do the Dr. B thing. Let's call that 1, let's call this 0, let's call this 2. Now we're going to be doing the derivation of what are called the Madelung equations. So I need to copy my notes because this is a little bit algebraically intensive. It's about 3 lines, so it shouldn't be that bad. But, okay, to put that into Euler equation, continuity equation form, we're going to basically do separation of variables, or something similar to separation of variables, except we're not separating variables, we're separating the real and complex parts of the wave function. So we're just gonna write psi in its complex polar form. And we'll write, I'm gonna just do this for the free particles to avoid clutter, but if we do that, then we have minus h bar squared over 2m plus v, or no, not plus v, times the second derivative, partial squared, partial x squared, acting on the magnitude times the phase. Again, for clutter, I'm not going to write as a function of x and t because that would make it really long. Is equal to I h bar times the time derivative of psi e to the I theta. Right? Okay. And if we separate this out, I'm going to do this algebra. If somebody wants me to explain this particular step, stop me, but I'm going to write basically two long lines. The first thing that I'll get is I h bar over 2m times e to the I theta partial squared psi norm partial x squared plus 2I times partial psi. So I'm just doing product rule on this thing twice. That's a 2. Sorry, that's not a 2, that's a partial. Partial psi, partial x.
H bar squared?
Actually, no. There is, I think I'm canceling it out here because it's a free particle, so it's like that.
Okay.
So this thing comes out front. Yeah, and then like the I is gonna, sorry, yeah, I'm skipping steps here, but I wanted to include the parts that are maybe possible to follow. So if you do this, plus I psi partial squared theta partial x squared minus, my handwriting is bad now, this partial squared theta partial x squared minus, oh, I just did that twice, sorry, minus psi times this guy squared, so that's like this, the first derivative squared, plus 2mv over I h bar times the norm of psi, and then is equal to e to the I theta times partial psi partial t plus I norm psi. And yeah, don't write this down unless you really want to. Okay, sorry, that's maybe not legible. That's I norm psi times partial theta with respect to t. This is a big long equation that you just get by expanding it out. But now we can reorganize it, cancel some terms, and basically put it in terms of like, we only have real things now. We have this guy and this guy, so we can reorganize it to a real and imaginary part. Yeah, is that, can people just accept that? How do we feel about that so far? All right.
So you write norm side just to indicate that that's really real.
That's the
part side.
imaginary. It's not the real part. It's the magnitude.
It's the magnitude.
It's like, yeah, because what I've said is psi is equal to its magnitude. Maybe I should have used a different notation for this. E to the I theta, where both of those, this is like magnitude of psi is a function of, say, position in time, and this theta is a function of position in time. So I'm substituting this into this, so this is really acting on that, and then just doing product rule twice for the spatial derivative, and then once for the time derivative. And then I just pulled some factors out. So now we have this big long expression that is just those terms separated out. There should be maybe a bracket there. Okay, so now we're going to group terms. So firstly, what we're going to do is group the real part, and I'm going to move everything over to the left side. So, well, okay, firstly I guess I can cancel these, that's nice. Right. So now I've gotten rid of the pesky exponentials. I'm going to put this guy is real. This is the partial with respect to time. here. So we have partial of this guy with respect to time, plus a term that goes and cancels out some 2's. So this guy has a 2, but there's an I here. So the i's, this I and this I cancel, so you get, yes, you should get a minus 1. Goodness. This term,
You maybe move the side T over on the left.
yeah, no, maybe it's the other way around. So, oh, I see. My bad. Sorry, I see what happened. I did this in my notes when sorry, I'm gonna move everything over to this side. Sorry. Let's do that. So, if we move all of these terms over to the other side, and then I'm gonna move this over here, but it's like I've really moved those over there. It's deep psi dt, and then this acts on this, and we can cancel a factor of 2, and because we moved over there, there's a minus sign, so this is plus h bar over m times this acting on this. The 2's cancel, the i's cancel, so we just get partial norm psi respect to x and partial theta respect to x plus this guy, where now I'm going to act this on this term, which again has picked up a minus sign, so the i's give you a positive, but I'm pulling in the factor of 2 times this second derivative. Okay.
Should the product include the potential energy in the real part?
Not, oh, you're right.
Because the I
Yeah.
factor.
Let's do that. That makes it easier. Okay, so you have this part, and this is the real part of it, plus the imaginary part, which is multiplied by I. This has an I, so again, I'm leaving this on this side. So this is just magnitude of psi times partial theta dt, and then plus this is h bar over 2m, and this just acts on this guy and this guy. We have the norm of psi times partial squared theta, partial x squared, no, sorry, squared, minus partial squared psi, partial x squared, and I think that is it. This is equal to 0. I guess you probably, okay, the video won't be able to see this, but you have, this isn't equal to 0. Okay, thank you for bearing with me there. You know, that's a lot of tedium. But now we've achieved the goal of separating a real and an imaginary part. And now is where the payoff comes. So does anybody, like, this is a hard thing to remember, I understand, but does anybody remember what the equation for the continuity, the probability current of the wave function was?
Some
Is
like
J-
the 1D over 3D.
Well, we're doing it in 1D, so say 1D.
You want it in like the imaginary form or like the side, like?
The imaginary form is a little bit nicer for this, but we could do both. So let's just say, what is the imaginary
I
form?
don't remember either.
Okay. Does this? Let's see if people agree with this. Times. Or sorry, not. I guess you can pull each bar over and out. Times the imaginary part of psi times the spatial derivative of its conjugate.
Yeah, something.
Does that seem familiar to people? Okay, and there was like a 2 before you had the imaginary, but then it's like twice the imaginary. So.
Yeah.
Okay. This thing can be written in an interesting way. If we plug in the form of psi here, you're going to get a magnitude, 2 magnitudes, right? So the magnitudes will just pop out of this, right? So you're going to get h bar over m times this guy, because, or sorry, not 2 magnitudes. You have this times its conjugate, so that will sort of pop out, right? Squared. and then times just whatever is left over from the like the product rule that you act on this. So you know what? I can just do it. let's just do it. Let's say let's say interlude here maybe. So J is equal to that. So we have h bar over m times the imaginary part of psi, norm psi e to the I theta, right? And then times the partial with respect to x. So that's going to give me partial this with respect to x, e to the I theta, plus partial theta with respect to x, e to the I theta, times, like this. This should be minus I theta. This should be a minus, that should be a minus, because it's the conjugate. Right, okay. Is that clear so far? And then this is going to cancel, but notice that this part doesn't matter at all, right? Because this part is imaginary and the phase will cancel. So this part doesn't matter at all because this part is real, right?
Yeah.
Should I maybe have, maybe I should, sorry. I think the convention that I want is this. So this would be minus plus like that. It doesn't really matter, but this is a little easier. So if we do this, the imaginary part is the only part that we care about. So this becomes h bar over m times the magnitude of psi squared, because you just multiply it. And then it's times this curious quantity, which is the derivative of this with respect to x. So derivative theta with respect to x. Okay. Now consider what exactly is the derivative of this quantity. Right? Can somebody, I think maybe it would be easier to do this. Can somebody tell me what the derivative of that is?
H bar over m times 2 times the magnitude of psi times d by dx.
Right, so h bar over m times, right, so 2 magnitude of psi partial respect to x, like that. And then plus
The product rule.
Right.
Psi squared.
and then just times. Yeah. Right.
What about the
That's right.
do you have to use the chain rule for the psi term?
Chain rule.
Because that's a function of x, right? So
Well, no, I mean, we're taking the derivative, right? Like you're saying you should take the derivative of x with respect to x. Because like that term,
okay.
yeah, because like the chain rule is the derivative of x with respect to x, that's just one.
Why are you taking the second derivative? I'm confused, sorry.
Well, because this is gonna become this.
Oh,
That's why.
putting it in there.
Yeah, because we identify, okay, I mean, okay, that's kind of spoilers, right? But now notice that, okay, so this thing can be written as, if we multiply through this guy by psi, or the magnitude of psi, so I do that, give you more room, f over m times magnitude of psi, and then this guy becomes a square, right? This is just, if we, or I guess let's say multiply by 2 psi, so 2, 2, and then this goes away. This is that, right? And then this is just the time derivative of psi squared, because of product rule. Yeah.
I think I missed it when you made the step from the probability current to the line below it.
This one?
Yeah. What were you saying?
Sorry.
about
This should be
Yeah.
erased. This was the part where I was like going to describe it, but I just decided to do that here. Ignore that part. Sorry, that was.
The probability current is h bar over m mod psi squared d theta dx. Is that it?
Yes, that's this guy. Sorry.
It's not equal.
Sorry, this is me. Yeah, I didn't have adequate time to practice this one, so sorry if it's more. Say this is J of X and T, and then that's maybe.
Now you're taking the derivative of J.
Okay, this is that clear now. That's good. Cream, you have questions?
Yeah. So did we just kind of like spawn in this big expression?
Like, what is the probability?
Like, what is the imaginary like thing in brackets? Like the first one that you wrote down.
That is the probability current, which if you're familiar with 115A, I don't know, does that seem familiar to you?
Yeah, but I've never seen this huge expression that you put inside the imaginary before. Or did you just like factor?
Oh, this was I factored
You
it.
literally just factored.
I
something
factored
out.
it, I wrote it in terms of polar form, like this. And then because it's in polar form, this derivative acts like a product rule. So this conjugate is this. And then this big thing is just the product
Okay,
rule acted on.
I see the step you made. Now. Yeah.
And then that's the probability current, so I wrote that here. And then if we take a derivative, we get this.
Yeah.
Okay.
Yeah.
So then the next step is I multiply through the real part, because the whole point is that this is equal to 0, so the real part and the imaginary part have to be equal to 0, so we can just multiply, right? So we multiply through by 2 psi, and then identify that this expression is this,
Okay.
right?
Yeah.
And then this guy is just the derivative of the probability density, because like derivative psi squared gives you a 2, and then it's twice. So this whole thing, which I know was kind of arduous to get here, becomes the familiar expression partial of mod psi squared partial t squared plus the derivative of j.
Maybe just one,
Yeah.
it's not t squared, is it?
That's correct. Yes. Yes, that's correct. This is the derivative of j of x and t is equal to 0, which is your familiar continuity equation. Now, if we want to put it really exactly in this form, say this would be a derivative, not a thing, you can just basically identify that, well, this is the mass density, right? But if we instead just think of rho as like a density, well, if we call, let's say define, I'll write it here. So if we define rho to be just the magnitude squared, which intuitively makes sense, right? Because it's not the mass density, but it's the probability density now. Then this thing becomes h bar over m, this thing becomes rho times this quantity h bar over m times partial theta with respect to x. And because it's like in continuity current form, we can simply identify that the velocity field of x and t, and maybe make sure that's clear, is just h bar over m partial theta with respect to x. So this one is now sort of a definition. Definitely a definition. Where this is this, so we can say that this is just equal to rho v. And this is now exactly in the form. So if I replace this, I can just write this as maybe partial rho times partial with respect to x of rho v. And that is exactly the continuity equation that we had here, except now it's not talking about mass densities in fluids, it's talking about the fluid probability density of the wave function and the thing that we identified now as the velocity field.
I'm still stuck. So when we took the derivative of j, you took the derivative of psi squared. Wouldn't we have to have an extra term of d mag psi dx when you do the chain rule? It's
Derivative of magnitude of psi.
because you take the derivative of the magnitude of psi squared. There should be 2 magnitude of psi times d mag psi dx. No?
Oh, you're right, but I also forgot to do that. So yeah, you're right. That's this thing here. Right. So that's just my mistake. Again, should be 2 magnitude of psi, mag psi dx, d theta dx. But now before it was wrong because this term wasn't identified. But now that's actually correct. Yeah, it's been a while since I've done a lot of algebra on the board, so thank you for putting up with that. Okay, so that's goal 1 accomplished. I think we'll definitely get to goal 2 by the end of this. We have a continuity equation. Now we need a dynamical equation, the Euler equation. That, as you may or may not suspect, is going to come from the imaginary part. So this one is, I think, definitely subtler, but it's not altogether more complicated. It's probably easier because we didn't have to identify this whole thing, because we've already identified the velocity field. So, okay, the thing that we're going to do that you might be a little bit concerned about is I'm going to divide out by psi. So I'm gonna say, let me divide out by psi. So if I cancel that, and then I'm gonna say this is a -1 over mod psi. Okay.
Good question. When we divide the continuity equation, we multiplied everything by 2 mag psi.
Yeah. So what I'm doing is this is a real part and an imaginary part.
Sure.
So in order for this to be equal to 0, the real part and imaginary part have to be independently 0. So I can just multiply the real part because it's like 2 equations that both have to be 0. Yeah, I understand that's going to be a little confusing. But now I'm going to just consider the imaginary part. And again, this also has to be equivalently equal to 0. And I'm going to do a slightly fishy thing, which is to divide out by psi, which may be concerning because psi can be 0, definitely. We will get to this in lecture 4, when this is a concern. But for now, just sort of accept that we're not going to concern ourselves with that.
Can you write psi equals 0 if you assume that psi equals mag psi e to the I theta? Is that?
Yeah, you can still definitely write it equal to 0, but you know the issue that we'll have is that then the phase is undefined.
Theta's
Right? That's the issue. Basically we have to insert one thing, but like I don't quite have enough time to go into it. We can maybe talk after, but that will be a topic. Yeah. So we're gonna do that though, and now all I need to do is just multiply through by minus h bar. So I'm gonna multiply through by minus h bar. Let me do that in yellow. And this becomes minus h bar squared. And then this becomes, yeah. So I just multiply through by minus h bar. And then I'm just gonna take this equation. So this equation here becomes, let me maybe give myself more room, of the form minus I h bar. Okay, yeah, I'll just write it cleaner so it's understandable. So minus h bar times the derivative of the phase. I'll get out of your way in a second. With respect to time, now let me just move this to the other side and get rid of the minus. So this is equal to h bar squared over 2m times this guy, but this thing is equal to, so this thing, let's maybe make that clear as well. This guy here can be written in terms of the velocity field. So let me say h bar squared, how do I do this? I said h bar over m times, okay, let me do this now. Partial with respect to theta with respect to t plus h bar over m times, so move that over, partial squared theta partial x, or partial theta partial x squared is equal to minus this thing, which is equal to minus h bar squared over 2m times, so this should be minus h bar, this should be minus h bar squared. I think this is all good. Do that. This is what? Minus h bar over 2m times the partial squared of psi partial x squared divided by the magnitude. Okay. Yeah, that seems correct. Sorry, I think that I'm going to do this step in a second. This seem okay? Just go from this to this.
Should there be 2 under 8 to next to n over?
Here?
No, but because they should have a same free factor.
Right.
and then one is 2 at the bottom and the other.
Yeah, you're saying this should be 2. I think that's right.
Right.
That's gonna be 1/2 mv squared.
Yes, this should be 1/2. So this does have this. Yeah. Okay. So yeah, there we go. Let's notice that this thing can be written in terms of the velocity field. This thing can be written, like Matthew kindly pointed out, as 1/2 m times v squared if I multiply through by minus h bar, so that becomes, or yeah, minus h bar. This becomes a minus h bar squared. This becomes like that. And this becomes 1/2 mv squared. So if I move this over to the other side, then I get the equation minus h bar times the partial of theta with respect to t is equal to 1/2 mv squared plus plus h bar squared over 2m times this quantity over psi. Okay? And at this point, I'm now going to, you can notice that this thing is now in the form of an energy. You could check if you wanted to, that this has units of energy. But it does. So this thing is kinetic energy plus some weird term, right? And if I were to have instead included the potential, or you know what, no, I'll do that in a second. If I were to have instead included the potential energy, it would have actually just ended up there as well. It basically, you could just carry it through because it doesn't really care, and then you would carry it through and you would get a like plus v of x and t term here. So I'm going to identify this thing as what I'm going to call the quantum potential.
Potential is in potential energy.
Yeah, Q. It's not really a potential energy, right? Because it actually depends on like the density of the wave function. So it's not quite there. It is a weird thing, which is going to be the only difference, seemingly pretty much the only difference between this and the actual fluid equation. So in the interest of not making you sit through so much more algebra, I'll just say that this is an equation that gives you conservation of energy for a density. So if you take the spatial derivative of this equation, which we will consider, then you will get the Euler equation. If you'd like to, I can work through that. It's only been an hour, so I'm not really crunching for time. But I don't know. Do people want to see that?
It makes sense.
Okay. So let me write down with the potential then. So here I just did this for the free particle, but I want to sort of have the nice set of two equations here on the board. If I had included the plus v term in the Schrodinger equation, then I would have just carried it through and plopped it in the imaginary part. And if I just plopped it in the imaginary part, then it would have come out and just been here. So we would have gotten this equation that looks like this. Minus h bar times the partial of theta with respect to t is equal to 1/2 mv squared plus v plus q. And then if you take the spatial gradient of that, if you just take a derivative with respect to x, then you will simply get the exact form that you want, which is that the mass times the derivative with respect to time plus v times partial x partial t partial with respect to x of the velocity field is equal to minus the gradient of v plus q. Okay. Yeah. If you want to see that, it's not. I don't know if I should. Do I do it explicitly in the notes? It's like a one-line thing. No, okay, I don't even do that in the notes, but it's pretty simple to just, you do another spatial derivative and then you get this.
Take the derivative of the whole thing.
Yeah, you take the derivative of this whole thing. And sorry, I guess this should be a spatial derivative. in 1D because it's 1D. Yeah.
One question.
Yes.
What's the motivation for defining our velocity field as h bar over m?
Two motivations. One is it gives you this form, so you can kind of identify it. The second thing that I think is maybe a little bit better to understand is this thing, where this we understood previously to be our probability current. So it's a current. And the current is the density times something, and that thing is going to be the velocity field. And it ends up being that also, you know, it works in this formula. So this is, I mean, you're right, I am defining it. This is not a thing you've seen before. Another way you could see this is if you instead define like the momentum field, and I just got rid of the m, then you could consider the momentum operator acting on this guy, and you would find that the not the eigenvalue, like the value that you get would be this. That I think is a homework problem. It's like pretty clear. So I guess the last thing that I should do with this derivation, before sort of getting into the Galilean invariance discussion, is
maybe can you just box them? Well, I guess just tell us the final equations. I mean,
sorry, these are the final equations.
those are the final equations.
These are the final equations that we're done.
Yeah,
These are the final equations. That's why I boxed them.
Thank you. Yeah.
Sorry. So let me maybe label them to. This is the continuity.
Yeah.
Yes, I should have prepared the organization of this better. This is the continuity equation. And this is the sort of, this is conservation of energy, and this is the Euler equation. The quantum, say, let's call it the Q Euler equation. Where this is identified with that one, the fluid equation, and this continuity equation is identified with this one. Okay, that, and then let me do the last thing, and then we can do one more pause. Because this guy looks like a conservation of energy equation, this is kinetic energy, this is what I'm calling the quantum potential, I'm going to do one last definition, which is a little bit less standard, but I think helps, and define this thing as the energy field, which we'll call epsilon of x and t. Epsilon of x and t is defined as minus h bar times the partial of theta with respect to time. Okay. I think that's everything. So now we have, this represents an energy field. See it? Do people feel comfortable with why we've defined this thing the way it is? Sorry, I know it's kind of skewed for you.
Yeah. It's hard to hard.
Yeah. Sorry, maybe if you want to move that over.
Because that corresponds to like potential energy in that equation.
So potential energy, if I had, right, so here I did it for the free particle, and then I said, if I just decided to include the potential, then I would have basically had an extra term that was V, like big V on this side. So that's this thing. And so I just go from this, I plop it here, and now I've identified Q. But,
Wouldn't your continuity equation also have to include V? Because you removed V from,
it does include V, right?
or are you talking about V, the potential? Is that?
Oh, no, actually no, because the potential is only attached to one term, so it would like, if you want to, I do work through that algebra in the notes, where the potential ends up only being in the imaginary part. So it just only is in this one. This is again big V.
And then what is epsilon?
Epsilon is the thing that I'm now identifying as, well, this looks like conservation of energy. This is clearly like a kinetic energy term. This is what would be this is the potential
So
energy
it's just
term.
energy as a function.
And this is the only new thing, the quantum potential, which is the only thing that's changed. The only difference between these two and those is that you have this Q here, right? But you know, even ignoring that, even with that, it still has units of energy. So I can identify that this quantity minus h bar times the partial of theta with respect to t is going to be my energy field of the quantum fluid. Importantly note that this quantum potential has a h bar in it, which means that in the h bar goes to 0 limit, which is the classical limit, right? Q goes to 0, and you literally just get like the normal equation. So in some sense, you can define, in certain cases, you can define the classical potential as when the quantum potential vanishes for something, which is equivalent to saying the h bar goes to 0. Okay, so it was a pretty long process to get here, but now we have our equations. They are nice, they look exactly how we want them to. Do people mind if I erase this part because I've already gotten the, does anybody want me to leave this up? I don't think.
I mean, is it worth saying that if you have a plane wave psi,
Yes.
is a complex fluid, which is e to the I px over h bar
Yes.
minus I omega t,
Right.
and then you take those derivatives of with respect to the theta, and you get v equals h bar over mp.
Right. So that's, yeah, I didn't say that because it's like a short homework problem, but
Oh, okay, so never mind.
yeah, yeah.
Sorry.
Because that's like a nice quick thing. Again, in the notes, there's a thing that I say in the appendix. Let me maybe clarify a bit more about what these things are. So, as you know, in quantum mechanics, you normally can't say, like in the sort of standard interpretation, you're saying like, well, we can't say unless it's a very specific thing that it's like an eigenstate of momentum or of velocity, which is a momentum over m. You can't say that a thing has, a state has a momentum, right? Because it really has like a superposition of those momentums, or it has a superposition of velocities. Or it has a superposition of energies, right, if it's not in an energy eigenstate. So I'm not saying that you can define a definite energy for them. Like there isn't a definite energy. Rather, if you were to take, so this is actually in the appendix, but like if you were to apply, say like the energy operator, which is the minus I times the time derivative on an energy eigenstate, you will find that this guy is a constant. So for an energy eigenstate, this thing is constant over the whole thing. So that's what, so for this thing to be constant over x means that it has a definite energy. For, if you are a momentum or velocity eigenstate, and you do this, acted on the wave, and you calculate this thing, you'll find that it's also, like remember, momentum eigenstate is e to the kx. Right? So if you take the derivative of theta, it's just k. Right? It's e to the ikx, and you take k. So this is a constant velocity field. So what we're basically doing is we're taking that, we're generalizing it to any type of distribution. We're saying, okay, now the superposition is kind of replaced by the idea that this is now like a thing that varies in space. So in the wave packet analogy, let's imagine that you want to think about a wave packet, for example, as like a superposition of plane waves. That's, I think, a thing that you should be familiar with. You can imagine that basically like this velocity field is saying where the prominence of like one wave is at the other, because it's like you make the velocity field by superposing a whole bunch of different constant velocities, and this sort of tells you where, like exactly how that superposition ends up giving you a total like spectrum, a total field of velocities that are flowing in every which way, which is what looks like a fluid. Okay, I hope that clears that up. This is definitely a little weirder because it's not what you're used to in 115A. But
also in a fluid, the energy isn't conserved.
The energy, well,
Is it? I mean, 'cause you ended up with three equations: continuity, Euler.
well, I got this thing is just from taking the derivative of this, right? So I mean, it's really
It's not independent.
It's not independent. The energy isn't conserved if you have like weird inelastic collisions in the fluid, right? Like, but I think that's not considered here because this is a pretty simple model where we're not doing Navier-Stokes here. We're doing yeah. And I think also because it's the velocity field, even thermal energy is probably, well, it's not accounted for here, but here energy is concerned. If maybe you could even say that this isn't energy conservation. Maybe you could just say that this is the definition of energy here, because I'm saying it's kinetic energy. Maybe the kinetic energy decreases for some reason. But that might happen because this thing it's like weird. But you know, V is going to give you a conservative force, so yeah, let's maybe even just say that this is more definition of energy. For nobody, I don't know if you might be the one that gets this right. This is like a Hamilton-Jacobi equation, right? So it's not. Yeah.
When you say it's constant, do you mean it's constant in space or time or in both?
This thing, sorry.
Oh,
You're
when
saying
you
a
when,
constant.
yeah, when you say that when it's an eigenstate or
It's just
velocity
it's a number.
for both space and time.
I mean, it's a number. Like if you, I mean, like yeah. Okay, so for example, what is the momentum eigenstate?
E to the ikx.
So what is the derivative of ikx with respect to x?
Hk or
I mean, just take a derivative of kx.
yeah.
Right, derivative of kx with respect to x is k. K is a number,
Yeah.
so it's a number.
Mhm.
Right? Yeah.
So, I mean, it should be the same thing really, but what we did is we derived the Q-Euler equation and we're formatting it in a kind of energy conservation way, whereas from fluid mechanics, it's not exactly
Yeah.
that.
Are you worried about like we're losing information?
Yeah, I don't know. I mean, is it one-to-one mapping? Is there like a...
It's not exactly one-to-one mapping, but I did this as more of an intuitive thing. You are right that the energy equation contains more information than the Euler equation, because when you take the derivative, you lose like constant shifts basically, right? So that is important. You can have a similar equation for a fluid this is like what they would call, say, without the Q, this is a first integral of motion, is what they would call it, right? I chose not to do it like that for the fluid discussion because it's a little bit more, it's a little bit longer. I mean, that would be, I think you could either start from conservation of energy or like a Lagrangian or something.
Okay, I see what you're
But
saying.
I just wanted to get that form so that you guys could then relate it to what we actually get in quantum mechanics, because those, especially the Euler equation, might not be immediately familiar to everyone, even if the continuity equation probably is. Okay, is that cool? Yeah, thank you for sitting through this. I know this is longer algebra, way different than last lecture. This is going to form the basis for our discussions later in the thing, so I really wanted to sort of hash out exactly how you get to it. Because this is now, this set of equations replaces the Schrodinger equation for us, at least for the time being. It is equivalent to the Schrodinger equations, and it replaces them. It replaces it very pretty much exactly, with the one caveat of this little pesky thing where we divided by psi, which we'll work about.
When you say it replaces the Schrodinger equations, you mean like the time dependent and time independent?
It's not really, I don't think you can draw a parallel between like the time dependent and the time independent.
Okay.
We did similar thing to separation of variables,
Yeah,
where we wrote it as a product. But one, this works for things that aren't separable states because you can always write psi in its polar
Sure,
form,
yeah.
right? Including the zeros. So it's actually, it's more general than doing a separation thing. Of course, the separation works because you can take linear combinations. But instead of time independent and dependent, we got continuity and dynamical equation, or Euler equation. My point is we're going to be working with this as the starting point instead of the Schrodinger equation. Sure. That's like, it replaces it because it's equivalent to it. So now we are sort of poised to answer the question of what went wrong with our Galilean invariance. Right, so this is sort of the punchline of the lecture, and it looks like we're right on time for it, so that's nice. So let me talk, I guess, I wrote that, so let me say, these guys are called, in the literature, this is the Madelung equations. Okay, that's the I think normally this is the one that you would call the Madelung in the literature. So it's a bit sloppy, but like that set is. Sorry, I thought I saw a question here.
Yeah, was it, is it, so you just answered it kind of, but
Yeah.
to clarify, it's not the continuity equation that's called the Madelung, or the bottom one, it's just the middle one?
No,
Oh,
sorry.
it's all,
sorry.
it's all three?
It's really these two.
Okay,
Is what
because the second one's.
Yeah, this one is like, this one I
Yeah.
did, but it's really these two, and
Yeah.
I can like, I don't have a good color. It's yolk, like that. There we go. Those are the Madelung equations. The ugly chalkboard right there. Okay, cool. I think I'm gonna move on to the last point of this discussion, which is the issue with Galilean invariance, which somehow we knew had to come from the problem that we said this. Now we are opposed to answer the question, how do we transform psi? Because, well, when you do a Galilean transformation, Galilean, oh gosh, let's see that. So, when you do a Galilean transformation, as we said before, right, we know that x goes to x prime equals x minus v naught t, ignoring like a constant, like an origin shift. But v changes now, right? V goes to v prime equals v minus v naught. And E, or let's call it energy because I defined it like this, energy goes to energy prime, which is equal to 1/2. For the free particle, remember, we're not considering, we're going to assume this is 0 because this would be an issue, but if this is 0, then the energy prime goes to, let me say T. Like, kinetic energy goes to 1/2 m times v minus v naught squared, which is equal to, what is it? It is, I guess I can just square this, but I want to make sure it goes to T minus m v naught v plus 1/2 m v naught squared, right? Where this is the change. So, okay, if we do that, then that just means that we can, well, these things are now identified. Importantly, I can say that this doesn't apply the energy because notice that all of these things are defined in terms of the phase. V is 0, so we don't care about it. And Q only depends on this guy, right? Q only depends on the magnitude. So since this is only going to change something about the phase, Q is invariant because it only depends on the magnitude. So we can say that this applies to E as well. And if you sort of, you can say this is like the spatial derivative, or sorry, this is the spatial derivative, this is the time derivative, and you integrate and then you sum up all of the extra contributions you need to add. We can say that this tells us that we need our theta field to go to theta minus mv naught over h bar times x plus 1/2 h bar times mv naught squared t. And yeah, I mean, I can do that, but I think you should be able to see where all of this comes from. I mean, like it's pretty simple. Like you just say this is h bar over m partial with respect to x, and you subtract v naught off of it. This is minus h bar partial with theta with respect to t. Subtract off of those things. Write this guy in terms of you have v, and then you get this transformation. And if you plug this transformation in, well, you could either go back to the Schrodinger equation and plug this into this form and then do all of the second derivatives and make it even longer, which I do in the notes, but instead we can even just ignore that and we can just say, well, what happens to the Madelung equations? The Madelung equations, well, this thing is simple. We know how the derivative transforms, so we have partial with respect to t prime. Right? We know that partial with respect to t prime is going to give us a, I guess I should have done it here. These should be primes. If this is t prime, then this is going to be a minus sign. I mean, this is going to be a plus sign instead of a minus sign because I'm rewriting it the other way. So partial with respect to t prime plus v naught partial with respect to x, acting on, say, rho is what we can call it from the Madelung equations, plus partial with respect to x or x prime, because that doesn't change, of rho times v minus v naught equals 0. And I think you can see that we get exactly, yep, so you can see exactly that this term and this term are going to cancel. Right, so this turns to 0, that goes to 0, and you just get back the original continuity equation. Right, that works because this is a constant, so this doesn't act. This just acts on rho, not v naught. Is that clear? Why that cancels? Okay. We can do the same thing for the Euler equation, or I will do it for this one. This is 0. This thing is unchanged. This thing changes, but it changes by the exact same amount, right? So if we just have minus h bar over minus h bar times partial theta with respect to t prime. Let's see, partial with respect to t. Partial with respect to t prime plus v naught partial with respect to x prime, right? Is equal to, and then theta is equal to 1/2 m v naught, or the mv squared, minus m v naught v plus 1/2 m v naught squared, and then plus v plus q, right? Or I guess not plus v, plus q. And this guy is going to give me v naught v, right? This is m times v naught v. So this term cancels with that. And let's see. Oh no, I needed to add to the theta. I needed to add this guy to theta. So this should become, this one's a little bit more complicated. I forgot. Yeah, this one's a little bit more complicated. You can say that it is, let's see, this is going to cancel with, okay, maybe do I want to do that? Shoot. Sorry, it's bad. Oh, I'm sorry, that's my fault. I did this poorly because I kind of was going to try to substitute two things. Because this thing is energy, so, sorry, let me rewrite. This isn't here. This is literally defined as the energy thing. So I can write, this thing would become energy and it would transform in exactly the same way. So I would have epsilon of x and t, and then just subtract off minus m v naught v plus 1/2 m v naught squared, and they literally trivially cancel, right? Okay, and then you just get back the original equation. Sorry, I should have done that. That was a bit of a mess up.
Can you explain where phi, the transformation from phi comes? I can't get
For
that.
phi?
Or for theta, sorry.
Yeah, I guess that I didn't explain super well. What you would do is you would say, well, this thing is h bar over m times the partial of theta with respect to x, and this is minus h bar partial theta with respect to t. This is approximately because there's the q, right? So I didn't include the potential terms, but the point is that you would take this equation, you'd say this is equal to that, and then integrate it with respect to x. That gives you one contribution, which will be this one. And then you do this for the same thing, integrate it with respect to t, and then you get the other term.
Sure. Okay, cool.
So my point is, if you wanted to plug this back into the Schrodinger equation and work through the very long algebra, which is kind of why we did this work, we've sort of pre-done the algebra, then you could do that and you would show that it works, but we can also just show that the Madelung equations are invariant because we transform the quantities correctly now. Yeah, sorry, this was, I got confused. Does this one make sense to people? Do you understand what I did here, where I literally just said, this is energy, and they transform, and then the transformations cancel out. Is that okay? Okay, so, yeah, that's, I guess, yeah, I'm about spending an hour and a half on these. That is the punchline of this lecture. that this thing, I guess you could say, is the punchline of this lecture, really, that in order to do a Galilean transformation, you need to transform the wave function in this very particular and not immediately obvious way unless you rewrite it like this. What it tells us is that transformations of coordinates seem to cause a phase transformation. And a phase transformation is non-trivial, right? This is like dependent on x and dependent on time. That is kind of a weird concept. So I use this lecture to introduce like why you have to do that. The next lecture what we're going to consider is basically what if you want to do this type of thing, but you want to make it more general. If you want to just say, change this isn't just some, mv naught x plus mv naught squared t. I want it to be theta plus alpha of x and t. It's any function, normal theta function. Can I do that? And the answer is no, but then we'll say, if I really want to do it, then I have to have electromagnetism. And that will be next lecture. Okay, I think that's everything. We're finishing at about the same time, so thank you very much for coming. And yeah, if there's any more questions, please feel free to ask them.